Okay, good morning, everybody. My name is Victor, and I'm going to be your anchor for this course. We are on the Cisco CyberOps cybersecurity training, which is a tier one level course for SOC analysts. It's a 28 module series, and we've just concluded from module one up to module 20. And the 21st course in the series is on cryptography. So the question is that why are we doing cryptography? Why are we trying to understand cryptography? Why is it so important that we understand how cryptography is being deployed to maintain either integrity or to authenticate people to be able to have access to data, our most important and critical asset. Now, I want to explain the role of cryptography in ensuring the integrity and authenticity of data. So, in cryptography, we want to be able to hash stuff to check compare hashes and see that nothing was tampered with. So s- cryptography based algorithms can be used to do all of those uh, um, hash checks. Authenticity. Now we want to use cryptographic encryption to be able to authenticate people and allow people into their systems or their data. Of course, most of the passwords they're going to be using, most of the passwords that we're going to be storing, we want to make sure that we don't just store them in plain text. We want to actually encrypt them. They want to explain how cryptographic approaches enhance data confidentiality. So we see CIA playing out in cryptography. Confidentiality. You have confidentiality, you have integrity, you have authenticity. So in confidentiality, we want to hide the data. That data, we don't want to store it in plain text. For instance, if you log on to an application or a website or even your Windows phone or your Mac phone or Mac PC, the thing is that your login password is not stored within those systems as plain text, so they're encrypted. Same thing for a website. By the time you're storing you put in your username, you put in your password, it authenticates you, allows you in, make data available for you. That's your password. It's not stored in plain text. They want people to understand public infrastructure. How can this be deployed across the public data, websites, web applications, networks, and the rest? Explain how the public infrastructure functions, where people need to share keys, where people need to collaborate, where you need to access a particular data, but you don't need to have a key per se. Explain how to use the cryptography effect, how to use the cryptography, how it affects cybersecurity operations. Okay, let's move on. Integrity and authenticity, securing communication. So organizations must provide support to secure the data internally as well as externally. The four elements of securing information or communications are: one, data integrity. You want to make sure that data is not altered. Throughout we run our digital forensics, most of the things we're looking at, most of the things we are considering, especially when you look at chain of custody, is that across the process, the journey through which data moves from one point to the other, you want to ensure data integrity. How do you ensure data integrity? Simply by checking hash functions for the file as it moves from point A to point B. So if the hash value changes depending on whichever cryptographic function that you use, you say that data has been tampered. It can just be introduction of a full stop, introduction of a comma, introduction of anything, right? No matter how slight that thing is, the hash value of that file is going to change. So that is a good advantage of how cryptography can aid data integrity. Same thing with origin authentication. We want to make sure that we guarantee that the message is not a forgery or actually comes from whom it states. We want to be sure that this data that is coming from so person. For instance, for a website, you see a website and it'll tell you you have SSL certificate is stored, but it's going to tell you who the certificate authority, who the issuer is, who it was issued to, and you can do most of these checks online, right? Data confidentiality guarantee that only authorized users can read the message. Of course, no repudiation. Okay, cryptographic hash functions. Like I said earlier on, you use hash to verify data integrity. We've done this practically during the digital forensic course. All you just need to do is use any tool, any application, put in a message. It's going to use a particular hash function. It will give you a hash value. So this hash value, you want to store it. Let's say if you have a letter, you can check the hash using the hash function, and you're going to get a hash value for it. If you give this letter to somebody, give it to anybody, tell people to look at it, tell people to scan and tell if there's anything that's not okay with it. At each point of the way, for each person that you give, you want to return back and still run same hash function on it. If you get same value, it then means the document was not tampered with. So anytime the data is changed or altered, the hash value also changes. It's a cryptographic hash function. So it looks like something like this. H small h equals to hx is used to explain the hash algorithm operates. I'll show you the figure. A hash function h, right, takes an input x and returns a fixed size string hash value h, right? So like we look at functions with respect to programming functions in mathematics. um it's going to have an input. It can be one figure, it can be two figure, it can be whatever, and it to perform an operation on it and return a value. X hash function hash value. Okay, so there are different types. You have MD5, you have SHA. So MD5 for MD5 hash, SHA1, SHA2, SHA3. So this is a little bit much older, followed by this, followed by this. So this is the next generation algorithm and should be used whenever possible. So these are a little bit old, right? So you can almost see by the bits, right? The bits tell you how secure they are. So you have 128 bit, you have 160 bit. Yeah, you see it's increasing. So that tells you how much security you can have using any of these functions. While hashing can be used to detect accidental changes, it cannot be used to guard against deliberate changes that are made by a threat actor. There's no unique identifying information that from a sender in the hash procedure. This means that anyone can compute a hash for any data as long as they have the correct hash function. However, hashing is vulnerable and man in the middle attacks does not provide security to transmit data. To provide integrity and origin authentication, something more is required. That's why we talked about defense in depth. So you don't use only cryptography, for instance. Like I said, I've seen websites implemented security using cryptography, SSL, and whatever, and still hacked. Foolproof, right? So you must make sure that you employ several defense mechanisms to protect your website, your cloud server, your email, your networks, and the rest. Origin authentication. So to add origin authentication and integrity assurance, use a keyed hash message authentication mode. So this is an additional secret key as an input to the hash function. So most deployments these days, uh, for instance, SSL, IPsec, SSH, they use this, right? So because people can always reverse engineer if you use just your normal what's it called, MD5, SHA5, SHA1, SHA2, SHA3, and the rest. So what is being done is that you have something else added to it, right? Before I encrypt this function, something is added to it. When the stuff is added, then you now get something else. So if you try going back, you're going to get something quite different. Okay, HMAC hashing algorithms. So an HMAC is calculated using a cryptographic algorithm that combines a cryptographic hash function with a secret key, right? Only the sender and receiver knows the secret key, and the output of the hash function depends on the input data and the secret key. So you add something to this guy so that you now have something at the end of the day. So you have an introduction of a secret key. Okay, so this is how you create, explanation of how it's been created, explanation of how it's being verified. So only the sender can verify that. So this is a classical example of how Cisco routers implement that in open shortest paths. First, that is the routing protocol. Let's look at, let me see if I can explain this to you. Uh, LSU is a link state update, right? So you have link state update, you have link state advertisement, and I think you have link state acknowledgement. So R1 calculates the hash value using the LSU message. So LSU message is what is my link state? So how am I connecting? What's my network? What's my IP address? What type of link do I have? What's the cost of the link? So for cost in OSPF, we're talking about what's the shortest path to get to a particular router or to get to a particular device. So it's a routing protocol that tells us how fast we can connect from one point to the other. And of course, when you see neighbors here, neighbors are just simply which router is close to me, which is my closest router. Because if this router is done, of course, this guy is going to be the guy that is going to be able to connect to the other PC, or this is going to now be a route to other device or the other data. So that's why it's called neighbor. So R1 is a neighbor to R2, R2 is a neighbor to R1. Okay. So there's a lab here you could look up. We'll look at most of this lab later on at the end of the course. Confidentiality. So data confidentiality is very important. And this brings us to two major types of encryption. So it's called the symmetric and it's called the asymmetric. I've considered this in one or two of the courses, but this is a more detailed guide with respect to cryptography. There are two main classes of encryption used to provide data confidentiality, and which is asymmetric and symmetric. These two classes differ in how they use keys. So one thing you should know is the difference between symmetric encryption and asymmetric encryption. For symmetric, they use same keys to encrypt and decrypt data. The key length is 40 to 256 bits, faster than asymmetric encryption, commonly used to encrypt bulk data such as VPN traffic. Now, this has its own advantages, has its own disadvantages. For instance, the key lengths are short. So I talked about key lengths earlier on, that the shorter the key length, the less secure it's going to be. But that helps us to makes it a very fast um, means of encryption, because you don't have long key length. It's just like somebody trying to break through a password, and the password is a short keyed password. Of course, it's faster to break. Now, for asymmetric, you use different keys to actually encrypt and decrypt, and the key length are actually long. So it makes it more secure, but it's more taxing than and therefore slower than asymmetric encryption. Commonly used for quick data transactions such as HTTPS when accessing or bank data. So it's more secured, it's slower. This is what was it called? Less secured, but it's faster. So they all have their different application. So this is how it works. So you have a data you want to what's it called, secure $1,000. You have a key, you encrypt it, you get this as a pre-shared key to these two guys. They all have this, so one key. That's why it's called symmetry. If you divide, they say you have symmetric beings, symmetric animals, symmetric items. So there are some items that are symmetric in nature. So if you divide them into two equal parts, what you have on the left is what you have on the right. So what you have here, what you use to encrypt here is also what you use in decrypting at the other end. end of the day, you still have your $1,000. Okay, so this is an explanation too. Same thing with this. So these are examples of symmetric encryptions. So you have DES, 3DES, AES, seal, rivest, ciphers. So you want to be able to understand and these symmetric encryption algorithms. There's so many of them. You want to know their description and how many bits they are or what range they are made up of and the application. Then the next thing you want to understand is asymmetric encryption. So for asymmetric encryption, we're saying that they also call public key algorithm are designed in a way that encryption and decryption keys are different, right? So their length is quite large, but they're a little bit slower than symmetric encryption. Now, if you see this plain text I have here, see the key I'm going to use to encrypt. See the gibberish text encrypted stuff I have. For me to decrypt, I got to use something else to be able to get back to the plain text. So that's the difference between symmetric and asymmetric encryption. Now, these are the examples. So you have Delphi-Hellman, you have digital signature standard, you have elliptic curve techniques, and their key length ranges, right? So you see they're a little bit much more secured because of their key length. Okay, so this is an example. Um, this is also explaining how data authentication can be done. There's also, I think there's a short video on the LMS that tells that simulates most of these things, so please look it up. This is how it's being used for data integrity. Diffie-Hellman is also asymmetric. It allows two computers to generate identical shared keys without having communicated before. Application is VPN SSH. You have different groups, you see, all up to 16 4096 bits, making it one of the most secured means of doing your encryption. Yeah, so there's a 4 minutes 29 seconds video that tells you to demonstrate data using hashing and encryption. So please make sure you watch it. If you have questions, don't forget to ask within the mentorship group. So there's a lab here encrypting messages with OpenSSL and decrypting OpenSSL. So there's also a lab on what's it called? Encryption of files. Now you know folder security is one application of encryption. You have most folder lock, file lock softwares. So this labs explains that. They also have telnet session in Wireshark, SSH session in Wireshark. You're going to see that most of this data, you see some in plain text, you see some encrypted. So how can Wireshark capture that? So Wireshark is going to capture that, but it's not going to capture that in plain text. So you're going to see the encrypted stuff on your what is being captured. So that's why we say Wireshark, for instance, and packet sniffing is we only catch guys that use plain text protocol. So if you use encrypted protocol and if you miss out password salting, addition of secret key, and that your encryption is not strong enough, then it's easy for someone to do reverse engineering. So public key cryptography. So the thing is that if we are to deploy encryption in the public space where people will need to use and verify integrity of either executable files, verify integrity of a website we are visiting, verify integrity of applications or data, then digital signature is one good application of public key cryptography. So digital signatures use asymmetric cryptography. So in digital signature, we say we want to provide authenticity, integrity, and non-repudiation. So code signing, the one that is most common is digital certificates for websites, right? So you see stuffs like SSL, you see stuffs like on your website, you see HTTPS. So you want to verify that this vendor is actually a good vendor, and when you submit your data as it's exchanging between you and the servers, you want to be sure that that data is encrypted and somebody cannot be sniffing through the network and capture that data. Then another way public key encryption or cryptography can be in use is code signing, right? So people can sign their files, their downloadable files, their their certificates, and several other things. So code signing and digital certificate is an application of what's it called? Public key cryptography, and these are the different algorithms that can be used: DSA, RSA, and ECDSA. Okay, so this is just an explanation of what I just said earlier on the last 2 minutes. So you want to ensure that that software you're using is from the publisher. The most of the times the executive files are wrapped in digital signed envelopes, which allows the end user to verify the signature before installing the software. So these are all applications of public key cryptography. Now, digital signatures for code signing. Look at the certificate you have on this site, right? Or on this device. File property, digital signature details, certificate information, certificate path, right? So you see, it's telling you it's valid from 3/4/2019 to 2021, right? And issued by this. So this is a certificate. Visit any website and tap on the green padlock. Click on the details or the properties of the certificate. You're going to see something exactly like this. So that's to say that the certificate has been signed. So you have some kind of assurance, and you can even verify this externally, right? You have certificate verification. Just put that on Google or say SSL checker. You put the website link there, and you can verify all of that. So that's one good application of digital signatures, or even a certificate, right? It's going to be digitally signed. Okay, so this is just an explanation of what we've been talking about. Look at Bob trying to confirm an order or trying to make a purchase. So it's going to be encrypted, it's going to be stored. By the time it's coming to pick it up, it's going to decrypt it, and you have data at the end of the day, right? So this is the signed data. Bob is confirming an order with Alice. Bob confirming an order with Alice, right? So, but before that is being done, Bob confirms the order and his computer creates a hash, right? So this hash has to be created first. The computer encrypts the data with Bob's private key. So you got Bob's private key, it encrypts it and gets this. The encrypted hash, which is digital signature, is added to the document, right? Added, and that is confirmed and sent to arrays over the internet. So this is application of public key cryptography. Okay, PKI Trust System. So we're saying that who is going to be providing this management? Who is going to be providing this infrastructure for us? So there's what we call public key management. When establishing an asymmetric connection between two hosts, the hosts will exchange their public key information. Trusted third parties on the internet validate the authenticity of this public key using digital certificates. The third party issues credentials that are difficult to forge. So you call this the public key infrastructure, which consists of specifications, systems, and tools that are used to create, manage, distribute, use, store, and revoke. That's why if your SSL, for instance, is expired, it's going to revoke your access to that particular site and tells you, do you want to access this particular website in an unencrypted manner? And don't forget that your data might be stolen. So it will not ensure authenticity for you. We will not be able to ensure confidentiality for you. We're saying that whatever data that you put into this website, people can sniff, people can pick all of this data, no confidentiality guaranteed. And cost certificate authority creates digital certificates by tying a public key to a confirmed identity such as a website or individual. Like most of the times when I install digital certificates on websites, you always see your certificate authority key. So that's what you enter within your panel to secure the website. Okay, so this is how it works. Priority. So you have different servers, different systems. So this number just tells you their class and their usage: 0, 1, 2, 3, 4, and 5. Trust system. So trust is very important. So this just tells you their topology, their level, and at what role they play. So you even have different public key infrastructure at different levels. It's just like registrars. It's just like an organogram for a computing for a company. So they don't all work at the same level, but they still deploy work. So single root PKI topology is the simplest. So on a larger networks, PKI may be linked with two basic architectures. So of course, this is cross-certified. So this is hierarchical CA topology, right? Where they all have relationship with each other. So interoperability of different KPI vendors. Yes, they interoperate, right? That's why they can verify themselves. That's why they can ensure access. For instance, if you implement SSL on using um, let's say DigiSat, it's a certificate authority, your browser or your network or ISP will be able to verify it, because no matter the vendor, they're able to uh, kind of authenticate, they're able to accept, they're able to verify most of these keys. So certificate enrollment, authentication, and revocation. So this revocation happens when either yours is expired or out of use, or if it's not originating from a trusted vendor, right? So one simple basic way to understand this is if a developer implements SSL on a website, right? Or implement TLS, or implement secured VPN. That will help you better understand most of these concepts. But they're very straightforward in the sense that we're saying that data from point A to point B, we want to ensure that they are secured. So we have to encrypt most of those data. But for us to do the encryption, we have to install certificates so that that data can be verified from time to time as being secured. Okay, certificate trusted by your browser. So your browser can decide that it doesn't trust a certificate because it doesn't know the originator. Don't forget, we're saying that where the certificate is originating from, uh, who is storing, who is accessing is very critical in acceptance. Okay, applications and impact of cryptography. So cryptography is applied in several areas: in SSL, TLS, in VPN, HTTPS traffic, networks, email, instant messaging, file system, code signing, two-factor authentication with smart card, securing USB devices. Even some devices, the USB devices have password systems. So that is one nice way they can have. You can implement cryptography. Encrypted network translation. So you see validity. So validity is very, very important. Signature validation error. So if a browser cannot validate a signature certificate, there's no assurance that the public key certificate is authentic. So what it's going to even do is going to reject you and tell you that your certificate is not trusted. The funnest part there is that it's going to even tell you that tell the user that the data might be compromised, data might be stolen, your password might be stolen. So it tells you in a very plain text manner what is going to happen since it doesn't trust certificate. And all certificates normally have a date range, validity. So normally you could purchase for a year or 2 or 3 years. And not just 3 years, you could purchase for as long as possible. Encryption and security monitoring. So we are saying that if you're monitoring a network, plain text protocols are not encrypted. So, but because they are not encrypted, they are not susceptible to sniffing. They are susceptible to people picking up on them, right? And that's going to make you a little bit vulnerable. So you don't want to use plain text protocol. So it's not easy to pick into a user traffic, right? Especially if you're using HTTPS, right? So the goal is you don't want to use HTTP, because if you use HTTP during security monitoring, your data can be seen, your data can be stolen. Okay, anything that makes sense here that I will have to explain to you that you're not able to grasp while looking at it? Okay, so that's all for cryptography. So cryptography is such a nice concept. You want to understand that there are different types of the goal of encryption, the goal of cryptography. And cryptography is simply the study of encryption, decryption of data. You want to have data, you want to ensure confidentiality, you want to ensure authenticity, you want to ensure non-repudiation. You want to make sure that you also authenticate. So cryptography helps our five elements of information security to be a success. So we can ensure that data that we have is not in plain text, it's encrypted. We can be sure that data we have, we can ensure integrity, that it's not tampered with. So that's where hashing comes in. Okay, so that's the end of the Cisco CyberOps Module 21 cryptography. So I'll see you in the next module.